Okay, for people who are joining this live stream, we are looking at some new machine learning functionality in Wolfram Language intended, I hope, for the next version. And let's see, Etienne, I think you're going to share your screen.
Yeah. Yeah, so it's function-supervised learning. The main function is learn distribution, which would be, okay, maybe I could now in the detail, I don't know. Anyway, something to learn the distribution from a list of data points. And then you can use the distribution to do various things, such as query the PDF, generate a sample. And from this function, there will be some
sort of kinds of different things. Okay, exactly. So let's see some examples of
missing imputation. Maybe just before, I don't know. I mean, I don't know the order. If we go directly in,
okay. I mean, learn distribution we've been working for ages. So go ahead.
Because there's a side thing that I want to talk right now, because otherwise we might forget. It's how we get information from arbitrary machine learning models.
Right. By the way, this information function, Sushma, maybe you know what's happened with this. There was this initiative to merge a bunch of these information functions. What has happened to that?
It is still on our queue. It's not just we don't have anyone to work on it right now.
I thought Itai was working on it.
No, Itai is not.
Yeah, that was. Yeah.
We need to get somebody to work on it. I mean, who?
Yes.
Who?
It was Xavier's project. We are trying to figure it out who will take it on.
I mean, we can all start putting up values for information. I mean, okay, maybe
yes.
Because of a design.
I don't know how difficult it is. I mean, so Sushma, is there a clear list of what needs to be implemented?
Yes, we have a list of things which are already implemented and things which we want to implement to make it like a finished product. But
is it difficult, or is it mostly just essentially plumbing?
I think Nick added no. I mean, I don't think so. It's difficult. I just think we need someone to actually spend some time working on it. But if like Etienne said, we can have multiple people add their own things to it. I mean, like has an up value. I can.
Yeah.
It's really agreeing on a style, right?
Yeah.
Which, I mean, I would vote for using the same style as what classify information has. Now we have a nice, it's called information panel that is in general utilities that everybody can use to do these sort of things easily. So
fine. By the way, if we're going to do that, those things that say 126 point examples per millisecond, that's really kind of goofy. We should remove those trailing points.
What do you mean? Oh, this point. Oh, yes, yeah. This one. Yes, it's true.
I mean, we should make sure that the number formatting stuff is set to not include those for these.
By the way, this is something I think Jose is working on a similar function, but I had to code something to make it human readable. To figure out, if it should say millisecond, in second, in whatever. Basically all these things. Or even
we have that information, and that's a. I think we need a function. There's a unit convert function which defaults to, SI. I suspect we need a function which does what Wolfram Alpha does, which is to produce the most reasonable form of the units.
Yes. I remember Jose said he thought about it. I'm not sure if he's working on it right now or not. But
okay, well, Sushma, maybe you could check that down because that's also a Michael type thing. I mean, it should be some kind of unit normalize or some such other function. Unit simplify. Maybe it's unit simplify.
Okay. Let me talk to Jose about it.
So about this, for sure, for 12, I want to use information because I don't want to add learn distribution information, animate information.
Right. So let's try to standardize the machine learning functions at least, and not have any more classifier information. And
exactly.
Let's try and get. Go ahead.
One design issue is that currently information also gives you information about a symbol, even if this symbol has a definition. Right? I mean, when you do information about sign, no problem. But this has no definition. I mean, has no own value. Sorry. Send has no own value, so that's all fine. But if I put, classifier equal.
No, I get it. It has a hold first attribute on information, which is probably
exactly. So if information of C will tell me C equal classifier function, like it will kind of override the value.
What does it do if you say information of f of x or f of 1 when f of 1 has a value? Does it deal with that in any sensible way? So just give f of 1 a value.
Yeah. No, it's not a symbol or valid string pattern. So actually, yeah.
Well, so there's an easy compatibility hack here, which is just to say, make it be a hold first and have it look and see if it's a symbol. I mean, I'm not sure whether we want to continue. I'm not sure anybody's using that behavior, but we could certainly continue that behavior and have it.
Yeah, a test if it corresponds to one of the special case. So it would evaluate, see if it's a learned distribution or the classifier.
Yeah, that's pretty horrifying.
If it's not, it gives information about the symbol.
That's horrifying. Didn't we have we talked about this in the design of the information function, did we not? I mean, it's conceivable as a design hack, we could have an info function, since in the last 30 years, the word info has become a bit more common than it was 30 years ago when it had to be called information. And we could then just, have that work the way we want it to work. Alternatively, we have to break compatibility, which I don't want to do with this information of A, although nobody kind of depended on it for programmatic purposes because it's what it's returning is pure print form.
Yeah.
And in fact, even that print form has changed over the years. So look, Sushma, can you get, it sounds to me like it needs another meeting, although maybe a meeting without me to go over what we can do with this.
Okay.
I think, the possibilities are, in terms of that design glitch, if we have to, we might have a thing called info.
Okay.
Although I would prefer to be able to use information, but we may have a compatibility issue there. All right. In terms of the, yeah, I mean, I'm not wild about, the way that thing says classifier information in big, bold letters at the top. It's not clear that that's the right graphic design, and I wouldn't mind looking at that again. But the rest of it seems fine, notwithstanding my comment about those trailing periods and things.
Yes.
Okay, so let's move on here. So you've got this. By the way, I wouldn't call it distribution information. I would call it learned distribution information in the header of that information block.
Yep. Okay. All right. Okay, so that's it for information. Okay, let's go to the meat of the meeting. All right, so okay, learning distribution. We could have, if we want, built-in distribution as well.
That would be good. Except that learned distribution is a very weird thing to say.
It's true.
I mean, it's not obvious that.
It's true. Actually, it could work just with learned distribution, and it will evaluate into another learned distribution that has.
Yeah, or it doesn't even need to do that. I mean, it could just, yes, it could evaluate. I think that's a better way to do it. I don't think, maybe as a courtesy, we can make learned distribution work with image string, but I wouldn't do it in general. Yeah. And I also think that's going to, end up being pretty funky because, like the space of all possible images, who knows? If you live on Neptune, it'll be very different. It's like if you live underwater.
Sure. Sure.
Yeah. I mean, I don't even know quite what that means. I think that rather.
Yeah.
So, a little bit like NetModel, I can imagine that we could have a bunch of distributions that are built-in distributions. So arguably, the way we should do it is that learned distribution should be able to take things, well, see, it's interesting. NetModel is something where we're taking, I mean, the question is, where will be our repository of distributions? Do we think we're going to end up with a repository of distributions?
Well, at first, I would imagine just documenting it in the in the like we did for classify.
Yes.
Then
No,
if it gets big, we have one page for each. If it gets huge, we get a repository. I don't know.
Well, but the question is, do we want something where we can, are there distributions that are going to be sort of arriving week by week that it's useful for us to be able to add to something?
I don't think so. I mean,
why do you say that? I mean, it seems like a distribution
Yeah, you're kind of right. It's true that there's a lot of activity there.
Well, and also for us, I mean, we've got lots of training sets, and it's like, okay, let's have aerial photographs. Let's have, some category. We've probably got the training data to train it.
Mm-hmm.
Now, to what extent, when we're using, I mean, are we using these as priors for other things, these learned distributions? Presumably we are.
They could be, yes.
Okay, fine. But anyway, let's take a look. Okay, so those are our methods. Is that right?
Yeah, that's methods.
And what's the default? Or it depends on the...
It will use the same automation as used for classify, as classify does.
Okay, so can you show me an example? Like, can you learn a distribution of cats?
Oh,
cat images?
Okay, sorry, I have to probably get back to a commit that is decent, because this was let's see. I mean, this, I think I was in the middle of changing stuff, and
okay.
Let's dash that and whatever, and distribution. And let's go back to, let's see. Where is it, Amir? Is it unsupervised learning 12? That will be fine?
Yes.
Sorry, I have to put the put the VPN. Okay, that should be a working one. And what could I show?
Well, let's just see some numbers first of all. So just say random.
Yeah. I mean, it's not over, but I could just do. Okay, I could do. Okay.
No, do MNIST. Do MNIST. Do
okay.
MNIST.
Yeah. Unfortunately, there's not many methods at the moment, but I'm going to grab any. Can do just a multi-normal. Resource data, MNIST. Okay. Fine.
Let's just say random sample.
First, I have to load the branch. Oops. My new branch. Hopefully. Oh, you know what? I should go in 11.3, because this one is like a. Let's just go there. Here you go.
By the way, why does it say importing the resource content? It should just say import resource content. That's a Sushma issue.
Mm-hmm. Okay.
Wait, is it loaded? What's going on? Yeah, I should have had that ready.
Okay, but the automatic selection stuff, so this is working now?
Yeah, I think it will. So...
Well, you would say random sample or something?
Yeah, I have to take... Oh, let's take... Yeah, whatever. Yeah, exactly. Let's do a random sample of, let's say, 10,000. Up. Sample, and I remove the tag.
Yep.
So now you have... and I think, okay, and if I do a learn distribution on the sample, I hope it is version. Oh dear, what's going on? Okay, maybe this branch wasn't so great after all.
Well, let's see what happens.
Yeah, you can see the learning curve going on, and oh, okay, it's using. You know what? Let me just use the multi. I think it's because it's trying a bunch of method. But not necessarily the best.
Table. What's that?
Yeah, so I'm going to just say use a multi-normal, and it will still optimize some hyperparameters. So something is a bit weird here. went to 0.
Okay.
I'm not sure what happened, but anyway. And then, okay, it's multi-normal, so it's not going to be a great thing, but I can do some random variate. So this, hopefully a Gaussian can be, I mean, yeah, I can do like some sort of digits.
Okay.
But, you know, even such a naive method like that is good enough to distinguish, you know, like if I say PDF is good enough to distinguish an anomaly. So if I take, okay, this is a training set, so I should really, okay, it's a bit cheating, but actually it's pretty high.
What the heck is 10 to the 58 doing in the PDF? Why isn't it normalized?
It's a numerical space, so it's not between 0 and 1, right? This can be, especially for high dimension, which by the way will lead me to, anyway, also design proposal. The PDF can be arbitrarily high or low, and often very low. So we should actually get a sample from the tests, from a test set, but I don't know.
So this is like a delta function. I mean, the 10 to the 58 is like the numerical value of some piece of a delta function in this giant space. Is that what you're saying?
I guess so, but let's take an element of a test set.
Put in PDF. Look, put in a picture of an elephant or something there in the second argument, and let's see whether it still says 10 to the 58. Just say picture of an elephant in the language. It's easy enough to do. Just do control equals picture of an elephant, picture of whatever you want.
All right.
You don't need to press the check mark. It'll just default, but it's more beautiful if you. Okay, there's an elephant. Now let's put the elephant in. Okay, that's encouraging. Why don't you black and whiteify the elephant? Just say, just say binarize or something in front of it.
Yeah.
Cool.
Difference. Yeah.
That elephant is not a digit.
It's not a digit, exactly. So I mean, that's why even with the stupid, you know, method, it's already quite good to distinguish anomalies. I mean, yeah, subtle anomaly is going to be bad, but you know,
there are better methods that are for images like real NVP.
Like,
so have you implemented that, or?
Yes, I can. Yes.
No, but have you?
Yeah. Well, okay. I mean, yes.
Yes,
we have implemented a neural network thing that can be quite better. But what we're really interested in is doing knowledge transfer in the same way as we do for classify and predict.
Yes.
Where you extract features, which is a really interesting topic because extracting features for learning distribution is kind of a different business than extracting feature for classify.
Yep.
For classify, you can extract whatever you want. For learning distribution, you need to have something that is reversible, and you need to be able to compute the kind of volume ratio of density by this transformation.
Yes.
I mean, there could be other ways to do knowledge transfer by fine-tuning a network or things like that, but we would love if we could keep the principle of extracting features. And so one of the projects we could do is to learn this transformation on, let's say, ImageNet. And there's a technique for that. So this is still non-volume preserving. I think I showed you the paper once.
Yeah, you showed me this one point.
And unfortunately, it's not something that will generate image as good as it can. So, you know, it's not state of the art, but it allows us to do a really good feature extractor. And we can just, you know, any feature we get, we pass it through the pipeline. We just learn the distribution on top, you know, and it should give something better. But I must say that knowledge transfer for learning distribution is quite of a, you know, research area. So
yeah, I'm not sure, but let's take a look. So your point there is, I mean, if we have certain categories where we can use that, just like we have for images, we have a base set of features, you know, images, typically anomalies in images are, you know, is there a break in this fence type thing, which is very different from the, you know.
Oh, yes, that will be using another type of.
Right, but I mean, is it the case that there's a base distribution? So I'm trying to understand. Do you imagine that you start from some base distribution, which is a distribution of all images, and then you're putting on top of it images of unbroken fences and broken fences and so on? Or mostly in this case, unbroken fences.
Unbroken, yes. That's the idea. That's the idea.
Right, but then what you're describing is that for certain categories like images, that we would have some base a priori distribution.
Yes.
That we learnt from, our curated, image identification set, et cetera, et cetera, et cetera.
Yeah.
Or whatever.
Yeah. And we just kind of modify the distribution to fit better the data that the user gave.
Right. Well, yeah, it sounds very sensible to do
that. But there's no paper that does that,
Well,
yet. So it's quite of a wild.
But why do we need? Okay, so this volume preserving thing is needed to have Jacobians going back and forth.
Yeah. So it's a neural network that is reversible and that you can compute very easily the Jacobian, the determinant of the Jacobian of the transformation. So
yeah.
So you have all the elements to query the PDF in the original.
This seems interesting, but let's just understand what the use cases are first, and maybe we get basic versions of those use cases and then improve them with this kind of technology.
And there's another benefit to like methods like RNVP, that it gives really normalized probabilities. It won't give these huge numbers if you query the probabilities.
What does it mean to give? I mean, but this is normalized, isn't it? I mean, if you integrated it over this space.
Yeah.
Yes. But it would be more smooth. I mean, you won't get like very high peaks.
Explain why.
Just that it's a parametric method. And so it will interpolate and extrapolate maybe better than some non-parametric. But even some non-parametric, you can make them smooth, like kernel density estimation. I mean, the kernel are smooth. So I'm not sure about this argument, but.
So wait a second. Why? Tell me why these numbers are so big here, and tell me why this other method will give more, modest numbers.
No, it won't give modest number. I don't think that. I mean, okay. Maybe what I was saying that it will less overfit. Like in that case, there seems to be a clear overfitting, which actually we could try by just this time. I'm going to be sure to separate a test set and a training set. So let's take the first 10,000 to train, and up. And let me quiet because apparently in my branch there's a bunch of messages. And
why did it go down to 0? What is the on the?
That's an issue on this branch. I think it's a thing that I solved in the branch that I'm currently working on.
Okay, fine.
I forgot what the issue was, but it was a bug. I mean, it's
so
tricky.
now let's see this.
Doing that is tricky. Yeah. Okay, it seems to have worked.
So why is there so much noise in the background of these things? Since none of the actual data has that kind of noise in the background.
True. And this is because of the method. The method isn't powerful enough. I mean, it's just a normal distribution in dimension 700, but still, and it's not powerful enough to do the digit.
But you'd think this the whatever this real.
Oh yeah. Yep.
Okay,
and even some others, even some kernel density estimation or other things that will give nice.
Okay, so of those methods you've listed, which ones are currently implemented?
This is done. This is kind of done, but we need to finish it. Kernel density, Amir can tell more. Like, I don't think it's finished, right?
It is kind of finished.
Okay, kind of finished. Good.
Yeah.
Gaussian mixture is done as well.
Yes,
multinormal is done. Real NVP is.
We're gonna make it better.
Yeah, but almost done. So the last.
was done. Yeah.
And NAID, we need to transform it, right? It was Georgia's implementation.
Yes, we need to transform.
But the big part, only random forest is really missing. Yeah, like we believe that you can do random forest in the same way that you can do for classify and predict, but for learn distribution.
Okay. And the auto selector between methods, have you figured that out?
Yes, that's kind of what I was showing there.
Okay.
I mean, there's one very interesting thing, which is always, Okay, so to select the best method is not just looking at the loss function. It's also using as how big is the model, how fast is the model, things like that. and it's always tricky to encode in a way the utility of a model given all these things.
Yep.
For classify, I think we found kind of a good thing. For learned distribution, it's sometimes learned distribution is learning 3 values, and sometimes it's learning 700 values, like here, or even more.
Yeah.
And so, as you see, when you have 700 values, that's a sort of PDF you get. So it's hard to say, do I prefer having my model, a twice better loss function, which is basically the likelihood on a test set, but on the same time, 50% bigger in memory? Am I happier with that?
But why isn't there a performance goal option?
There is. So there's performance goal, memory, but even with the performance goal, we want to be able to give decent,
So you want to have finer control than just saying optimize for memory?
Not necessarily finer control. I just want something that makes sense for users. I want to try to figure out
what the trade-offs are.
Yeah, exactly. What the trade-off are, exactly. And this needs still a bit of work from my end to figure out.
Well, let's think about that. Look, let's think about that in the, ultimately you want a sort of utility function for users.
Yeah.
That is what, and, that might depend on what the users are using it for. That might depend on their computers, might depend on a bunch of things. But what's the general theory? I mean, if a user could meaningfully define their utility function and feed it in as a function, for example, what will we do with it? See what I'm saying? So in other words, let's imagine that a user, that the performance goal could be, take an association, which says how much memory each thing is going to take, how much this it's going to take, how much that it's going to take.
True.
See what I'm saying?
Yes. Actually, we have time goal already, which is do in 40 seconds. We could have similar things for memory goal, or I don't know.
Well, it's a possibility, but I mean, the most parameterized version would be just for every candidate method, generate an association that says how much memory it's going to take, how long it's going to take, etc., and then have the user define a utility function that says, I care. Now it may be completely unrealistic for users to define that.
Yeah.
And then so then what will happen is we'll end up with a bunch of named performance goals yet again, which is what we already have. But what you may be saying is that that we need shades of named performance goals, a little different than just optimize for memory, optimize for speed.
Yeah, I think this is it's notoriously very hard for people to express their utility, in a mathematical way. I feel that probably boundaries is the best.
Yeah, which is like time goal or something.
Yeah, I want the one that has the lowest loss, but it shouldn't be larger than this amount of memory.
Fair enough.
But it should be at least this amount of fast to evaluate. I think
that's reasonable. That's a good idea, actually. So how would we represent that?
Yeah, exactly. Yeah.
So I think it's part of performance goal. So let's imagine that we had, and then we had an association: max time, max memory, arrow, whatever.
It would be max sampling time, for example.
This is a good idea to do something like this, because it could be the case that sorry, you can't do it with that performance goal. In which case it generates a message and does the best it can. But this is a good idea. And I wonder whether that is relevant for other, that's probably relevant for other functions that use performance goal as well. I really like this idea, actually, because
your max model memory,
or whatever. Yeah, I mean, it's got to be qualified in some way. I don't think it's just max memory, because that's
yeah, you can talk about the training. Yeah,
I like this idea. We should pursue this idea. But let's go back to the main discussion.
Actually, just to give you an idea, that's the sort of thing that we measure. That was the model information about the best model. That's kind of don't know if I ever showed you.
No, I've not seen these.
This is inside the classifier. I mean, or whatever model you can go, and there's a training information, and it kind of show all the configuration that have been tested. So here it's all the same method, multi-normal, but a different value for intrinsic dimension and.
That's really interesting.
And so you can have a look at the history of everything.
Why has the model utility got such a weird? Why is that? What's happening there?
The model utility, well,
why is there a big space in that column?
Oh, this I don't know what this dot is doing here. I have no idea. Oh, it must be the.
It looks dotty, so to speak.
Yeah, I think it's a display problem because I think it's just one file.
I think that's for you to try and track down and something's wrong there.
Yeah.
Okay, but anyway, so
all right, yeah,
that's very nice. Okay, let's go back to the main thread here because I want to get to anomaly detection.
Yes. Okay, so you have the learned distribution, and then
all right. So I'm strongly suggesting that this learned distribution thing, that we try and train it on some things like images, aerial photographs, whatever else, which shouldn't be very difficult to do. I mean, we have those training sets.
Yeah. And
so let's get some named distributions learned.
And which actually will overlap with named anomaly detector, named missing imputer.
Yes, exactly. Okay, so let's keep going.
Okay, so PDF, same as what PDF is doing now, except you cannot do a symbolic evaluation. I mean, symbolic,
tough luck. PDF.
Yeah, right. We could probably introduce a log PDF because as you just saw right now, 10 to the 58, 10 to the minus 281, and on real image is going to be worse than that. So log PDF would make sense.
Well, why don't you just say log of the PDF?
Because of the precision issue.
Oh, you mean to say that we'll actually run out of machine precision bits?
Yes. So it could return in arbitrary precision.
I think it should. Why not? We have arbitrary precision. Why not do that?
Yep.
I think that's a better idea. I mean, unless we think, I mean, these numbers are pretty non-meaningful anyway. You should talk to Roger about log PDF. I don't think it's great. I think unless he thinks there's some other reason in the world of statistics to have a log PDF, I would suggest we don't do it.
Okay. Maybe we just don't document it.
Well, you can put it in some hidden context somewhere.
Yeah.
Okay. Random variate.
Random variate. Okay, so to get a new example, it's exactly the same as the current random variate.
Great.
This is optional. Maybe I talk after.
Okay.
I talk about
let's look at anomaly detection.
So, all right. So the goal here, anomaly detector for arbitrary anomalies. So we kind of, no explicit information at least about what anomalies are. So it's purely unsupervised. Right.
Although you might have a prior distribution.
Well, not of the anomalies, but basically the idea is to learn
prior distribution of what the normal behavior is.
Exactly. That's the thing that you learn from the data. So learn, that's what I should have, right? Learn distribution from the normal data. Okay, very important. Yep. And actually, okay, we're going to talk about it just afterward. And then to tell that something is an anomaly, you compute its PDF, and then you look in which percentile this PDF falls if the data were normal. So for the normal distribution. I understand. And if it's below a threshold, then it's an anomaly. And I mean, okay.
Boy, p-values, the overused p-values of medical research and other kinds of areas, right again.
It's kind of an extension of the classic p-value. So we have potentially other name for it. I mean, we're going to talk about it just after, but I mean, the fact is, okay, the idea is just to have a threshold on the PDF, right? Yeah. But to communicate with the user, so we're going to go it just afterward. Yeah. So the user can set this threshold. It's not nice to have a PDF threshold because you see the kind of value PDF gives. So it's better to have a sort of p-value. And if you put something like 0.01, It means that if the data falls in the first percentile, of the less likely data, then it's considered anomalous. But we're not sure if we should call it, because p-value, I mean, actually, when we started designing this with Amir,
I don't understand why it's called p-value. Why isn't it just probability?
We could call it probability threshold as well.
Which seems a lot more easy to understand.
But, okay. But it's not the probability to be an anomaly. That's very important.
No, I understand. It's the probability okay, so the issue is what counts as an anomaly? If the probability that this should happen is less than 0.01, then consider it an anomaly, right?
Exactly.
Okay.
Exactly. And this might be a bit, for example, when you use, okay, so this is about training, let's go directly to using the detector. You can ask for the p-value, and this might be confusing. If you ask for the probability, people might say, oh, there's a 2% of chance it's an anomaly, which is not true. It's not 2% of chance it's an anomaly.
I understand. Okay, yeah. So look, what you were trying to, to talk about, I get it. So it's if the word normal wasn't used for a different purpose, really what this is the probability under normal conditions, under ordinary conditions, that you will get this.
Yeah, exactly. And so, I don't know if it should be like...
Well, the word expected probability might be a better way to... If you call it expected probability, right? Expected as in expected when you don't, anomaly is, I don't know why I'm thinking of the nobody expects the Spanish Inquisition silly line, but an anomaly is what you don't expect.
Yeah.
Right. I mean, okay, so why don't you write that down? Expected probability threshold in your list there.
Yep.
I mean, I'm not sure it's right, but you get what I'm saying? Because then what you could say is anomaly detector, blah, 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 expected probability. An expected probability, people won't think that means the probability that it is
it's a bit like a mean probability.
I know. So that doesn't seem right. Someone on the live stream is saying, just call it threshold. Yeah. The problem is that we have to name this other case, which is extracting from the anomaly detector
exactly
what the ordinary probability is for that situation.
Yeah. Abnormality value.
No, but it's not the abnormality. That's the whole point.
Actually, it's the
normality value.
You're right.
By the way, someone else asked on the live stream, is it going to be possible to do stochastic variational inference, which I don't know what it is. Do you know what that is?
I mean, this is a high-level automatic function. So you'll use methods that can be a variational autoencoder. Actually, we have a version of variational autoencoder, but we're not going to use it straight away because it's not a method that you can compute the PDF in a blink of an eye. It's good at generating, though. So I guess we will add to this list of methods, we'll add a bunch. Like these are they're good at everything. Mm-hmm. You can sample fast, you can query the PDF fast, the PDF is exact. But then you have this whole slew of other methods where the PDF is slow to be computed, or the sample is slow to be computed, or the PDF is approximate.
Yes.
All these sort of things, like like Boltzmann machines and even GAN. GAN, you can generate well the data. It's fast. Mm-hmm. You cannot compute the PDF. You can just compute a score that is somewhat related to the PDF.
Well, what do we also do? If you ask for a PDF of a line distribution in a GAN generated thing,
I think it just won't be in the automatic thing. So all of this will be automatic.
Yep.
And then you probably have GAN that the user can specify, and they will know that if they use a GAN, they won't be able to get a PDF. So that's why for the first version, we just focus on this one. It's easy to make them play nice together in the same automation procedure.
Right.
And then we'll add the kind of the one that need to play on their own. Because we can compare. Okay, what's very important, since they can all compute the PDF, we can compare them.
Yes.
Compare GAN with a Wolfram machine with one of these is hard.
Yeah, right. Okay, let's keep going here.
Okay.
So we've got a question here about what we're calling these thresholds and so on. But let's just try to understand anomaly detection of a bunch of examples gives an anomaly detector. But so I don't understand why there isn't an anomaly detect where there are a bunch of samples and then a value.
Yeah, so that's the other functions. So we thought about something called delete anomalies.
Well, that's nice, but I'm suggesting for your main function, instead of calling it, okay, so let's look at the classify example. We've got classify and we've got classifier function, right? Am I making sense?
Yeah.
So why isn't this anomaly detect an anomaly detector function? Why aren't those the names?
Oh, that's, yeah, could be.
Because anomaly detect, that's perfectly fine to say, well, here, if you say anomaly detect, there are a bunch of examples, and then the second argument could perfectly well be a bunch of samples, and you just say, which of these are anomalies? Well, I don't know. What does anomaly detection?
No, I agree. This was kind of to follow the other unsupervised learning function, which was, feature extraction, dimension reduction, learn distribution, because all of the unsupervised learning have the fact of these shared properties that you can either learn something or apply to the data at hand. You see what I mean? Like these find anomalies will actually, or delete anomalies, will actually work on the data given. They will train on the data, and which is actually an interesting problem, because it means that there's a sort of a chicken and egg thing. Because we want to learn on normal data, but we don't have access to normal data. So the strategy is to start with a subset of data that we're quite confident they are normal, and we train on that. And then we add, in incremental ways, the data point that we think are the most normal. And so it's a bit like clustering. So that's kind of why we followed the detection.
So hold on. Let's walk through this a moment. Okay, so you think, I could imagine it's not fast enough, basically, to just say anomaly detect of 1,000 things, comma, one thing. For example, okay, let's give a crazy case. Let's say, I don't know, you're trying to work out did this person, what's a good case? Did this person really walk up the mountain with their pedometer, or did they simply put their pedometer on some machine? Okay. And it's a one-shot thing. You've got, you're not pre-training. You're just saying, here are 1,000 cases where we know it was okay. Now tell us about this one case.
Okay, that leads to an important thing, is that here we do not explicitly say the one that we believe are okay.
I understand. But why don't you just only give the ones that you believe are okay?
Sorry?
No, wait a minute. Is it useful? Can you learn anomalies better if you can say, these are the ones we think are okay, these are the ones we think aren't okay? Then it's more like a classifier.
You won't look at the one that you think are not okay. You will only look at the one you think are okay. But it is useful, because then you don't have the question, should I discard some to train my distribution? You just take all of them, you learn distribution, and you're done. So it has some value. But one thing that is important is that we never look at the anomalies, because we assume that the space of anomalies is so large that we cannot learn anything from it.
Yeah.
So that's something we started at some point, some routes. Let's try to get some information about the anomalies and so on, and then we figured out it's classify.
Yeah,
so,
right. Right. So, you know, the claim is the anomalies are rare, and if you learn if you learn from a bunch of examples, even though that might contain some anomalies, you're still asking, so if the anomalies were happening 10% of the time, it's hopeless.
Not necessarily, because we have this strategy of kind of growing by starting with the data that is the safest.
Yeah, well, that's a weird controlling it. But I'm saying in the general case, if you've got enough data and less than 0.1% of it is anomalous, you just feed the whole thing in, including the anomalies.
Oh, yeah, this will be fine. Yeah.
Right. I think that will be the most common case here.
There's something we need to be careful of is a repetition of an anomaly, because anomalies are very rare, but for some reason, because something is, something is broken and starts suddenly generating crazy measurements, but it generates the same few times.
Well, so let's look at a use case that we'll have, okay, which is monitoring a bunch of our servers, okay? Generate a bunch of stuff, generate log files, all these kinds of things. We pretty much know things are not, we know what it means to be operating nominally, so to speak. So, we just won't train it on things where we know that the whole thing was broken.
Yes, yes.
Although there will be lots of ups and downs, even as we, okay, but let's keep going.
And actually, okay, very related. There's an option we're thinking of putting, which is called anomaly, either anomaly frequency or anomaly fraction. We don't have an idea, but basically, it's a user that estimates the frequency of anomalies in the training data. Very important. They don't say anything about the test data, but they just say in the data that I give you, I believe there's about 1% of anomaly or 0%. So actually, the case where you put only good data, it will put 0%.
That's a horrible name for that option.
What could we do else?
I'm not sure. I mean, these are what will be an analogous thing. Gosh. See, anomaly frequency just suggests that is the expected. I mean, what you're saying there is that's the frequency of anomalies in the input training data.
Exactly.
Let's keep looking at some more of the stuff you have here, just to understand.
All right, there's a pay threshold. Then the idea, okay, when you use a detector, it will be like classifier, true, false, except you cannot ask a probability, but you ask some p-value type thing instead. These are detail. And then we thought about
Are you sure you want true, false? Are you sure we don't want? Yeah, I guess we need that. I guess we need that because then we can do a select on that. But I mean,
yeah, exactly. And
I mean, I'm wondering if we want a function called anomaly probability rather than having to ask for specifically for the probability there. I mean, it seems like it's a generally useful thing. What's the chance that this is anomalous? It seems like that's what people will want to ask a lot of the time.
They will, but we cannot give that. We cannot give that.
Why?
Because we don't know anything about the distribution of the anomalies. So this, we would go back to classify. Classify can do that because you give information about class A and class B. But here we don't use anything about the anomalies, so we cannot tell probability.
But what the heck is that then?
This is the p-value. So that's what you were saying exactly before, right? If everything was normal, the probability to have something worse, I mean, less likely than this example is.
I understand, but what's wrong with calling that anomaly probability? That's the probability that this example is anomalous.
No. It's not.
It's the probability that in the ordinary distribution, something could be further away than this.
Exactly. Which is not the probability of anomaly.
I see. It's the probability of it not being an anomaly. So it's not even that. And that would be one minus.
Yeah. It's if all the anomalies lives very, very far in the PDF, then actually, even if you have a p-value of 0.01, the actual probability of being an anomaly is 10 minus 10. Because actual anomalies have a PDF that is much, 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 much lower.
I didn't quite understand that.
So,
I see. I mean, this thing, yeah. I see. I understand. The actual anomalies are far away, but you are still, yeah, I get it. Okay, let's just see to the end of your thing.
So then we're thinking
delete anomalies. That's interesting.
Exactly. Which basically would,
That's interesting and can be used quite generally.
And
dangerous as it is.
And we're thinking of the possibility as a first argument to put an anomaly detector inside, or to use it as like one of the built-in.
Well, so you're saying that there's the normal case is there's just data there, and it learns the anomalies,
and applies to data. Exactly.
But in the other case, I mean, that could be an option for the anomaly detector.
Yeah.
But it's kind of an external. It's a little weird that there's a two-argument thing there. You can't call it an anomaly detector. Yeah. It's already a thing. It's right now.
It's need to be the detector function. Yes. If it's a function, as we said before. Yeah, it should be function, of course.
I think so.
And okay, it could be. Actually, this is very interesting because for classify and predict, you might want to have an anomaly detector.
Yes.
Although,
what exactly would you do with it?
It would return anomalies when you do classify, and you put, that's a classic thing, right? That you actually been asking for a while. If I do something like that,
right?
Because there's no anomaly detector, it will
tell it's
Esperanto, where it could return.
Well, what would you like that to return?
I mean, the simple solution would be indeterminate or missing anomalies.
Yeah, I mean, anomalous is a kind of a strange. It's probably not a language. I mean, missing, not recognized would be a better. I mean, that would be more user sort of oriented.
Yeah,
that would be one word. It will be cameled.
Yeah,
not recognized. I think that would be the better thing.
Yeah,
missing, not recognized.
Yeah, and I guess we could, by default, actually, when we have this detector anomaly, all classify will train a very naive anomaly detector. And then probably it will be a bit conservative, right? Because if the user wants to classify that, actually we should need something to inhibit this. If the probably a way to change the threshold, actually we'd probably change which also makes have a consequence that we should probably put anomaly in the name, because putting something like p-value threshold here is quite obscure in the context of classify.
Utterly obscure.
So it would be anomalous threshold, or I don't know.
Okay, sorry, let's go back here. I don't even know what anomaly. I mean, I don't know what that. Well, it would be probably anomaly detection threshold would be a more reasonable term, I think. Anomaly.
Yeah.
Anomaly identification threshold. Possibly.
And I guess we should use the same for here.
Wait a minute. What is that? That's no. That's a function.
Oh, sorry. Anomaly frequency. Sorry, I'm put at the wrong place here.
Yes. So what would it be? Anomaly.
And it would just.
I think that would be. Look, that would be. So first of all, I'm suggesting that function is anomaly detect, not anomaly detection.
We can because because I mean, we thought about doing an anomaly detect, but probably doing a find anomalies is better because we want to have something that gives positions, this sort of stuff.
Mm-hmm.
So instead of doing anomaly position, find anomalies. I mean, maybe we thought we just put a find anomaly and some property.
Yeah, possibly.
And it could be replaced by a anomaly detector as well, but we are quite. I mean, I think I would privilege the solution with the delete anomalies and just a find anomalies that is a one-shot function that is, Swiss Army. Swiss Army one-shot function. And this is just a simple delete.
Yes. Right, but anyway, so what are you suggesting with respect to anomaly detection?
Then I think that's fine to change in anomaly detect if we think it's better. I mean,
but it would be more compatible with like dimension reduction that returns a dimension reducer function and dimension reduce, which only return the reduced vector. We would have anomaly detection, which returns a function, and anomaly detect, which returns the anomalies.
Yeah, but classify, for example, returns. The point is that anomaly detect could have a 2-argument form which actually does the anomaly thing, just like classify has a 2-argument form that actually does the classification.
Although I must say we'd never use a 2-argument form. In retrospect, I would have been, like if classify was actually classification, it wouldn't be that bad.
Fair enough. Maybe this should stay as anomaly detection. I'm not sure. So, listen, we're running out of time here. This probably should have been a longer meeting. What is generate new examples? Data generate, data synthesize. Why is that different from learn distribution and then?
Well, okay. So learn distribution is kind of a generic function. But let's say somebody just wants to generate data. They use data generate, data synthesize, or whatever name we call it. And then we can already grab the method that are good at that. For example, again.
Yes, I understand. Right. I mean, that's something like, dream and image type thing. Is that right?
It's, sorry?
Dream and image.
Oh, yes, exactly.
But you might need a seed for that.
I mean, okay, that's another thing. You mean like to condition, to have like some sort of yes. This is getting, this asking more question about the design and about what the future of predict. May predict can, and this is the whole realm of conditional distribution. So here we kind of limit ourselves to non-conditioned distribution, but we could imagine this whole thing to have some condition. So here I will put learn distribution, cat, right? Oops.
Mm-hmm.
And so on. And Yeah.
We should discuss this another time. But this is
but I think it's not contradictory. There's some design that fits well with this current design.
Right. Can we pick this up again, like tomorrow-ish? I mean, we've got some momentum here. Let's try to get this finished. I don't
tomorrow-ish.
Well, I don't know. Let's let Eric figure that out. Okay. I don't know.
Okay. I'm pretty busy. Yeah, but yeah. Okay. Good.
Okay.